All right, quick review of what we did yesterday. Without a good foundation from yesterday, today's going to be a little hazy. So let's make sure that we're clear on everything that we talked about yesterday. All right, so some guiding questions that we had for your homework, okay, is the relationship between monomers and polymers. And we talked that monomers link together to form polymers. And this whole unit is about polymers. And then today, what we're going to be taking a look at is how the structure of the polymers affect the physical characteristics. So your objective for today, students will learn how the structure of a polymer affects its physical properties. So, yesterday in class we talked about how polymers can take on different structures. Anybody care to volunteer one difference in structure a polymer can have? Taylor.
Could be polymer chain length in general, so whether it's short or whether
Okay,
it's
so
longer.
when we talk about chain length, so how long is that polymer chain? And we talked yesterday, generally, are these short, long? Do you have a number?
Long, usually in the thousands.
Okay, they can be in the hundreds, thousands. Polymer chains can be in the millions. Okay, they can be in the millions. One other. And somebody give me one other property. Shannon.
Side chain.
Side chain. So what would a side chain look like?
So if you have like the zigzag thing, it goes off the vertices.
Okay. So off one of the carbons. Okay, so you have side chains, and we could call side chains what else? We call them branches, okay? And it looks just like that. If you have a tree, you have branches which come off that main trunk. Okay, so we have that main chain, and off that main chain, you can have a lot of different side chains. And one more, we're looking for one more, Brian.
Cross-linking.
Cross-linking. And what does cross-linking do?
Bond separate chains together.
Okay, so you have a chain, and the cross-links are these bonds that will form between them. Okay? Now, we haven't actually talked yet about what these things are going to do and how they're going to change the physical properties. Okay, and that's what we're going to talk about today. So what are some of the physical properties that we talked about yesterday that we're going to be investigating today? Physical properties. Somebody else besides Brian. Matt.
Hardness.
Hardness. So how hard a polymer is, okay? And you've probably seen polymers, plastics, okay? If you've ever had synthetic decking, yes? Those are made of plastics, polymers. And those things are very hard. Whereas opposed to a water bottle, which may be at your table right now, not so much, not as much, okay? What other property, Sebastian?
Plasticity.
Plasticity, okay? So plasticity, that's one thing. And plasticity is where the term plastics came from. Elasticity. When we think of elasticity, of course, we think of a rubber band. Stretches, goes back. And one more we're looking for, other than the standards.
Tensile strength.
Tensile strength. Remember what that is? No? Think of a wire or a rope. If you pull on a rope, eventually what will happen?
It'll rip.
It'll break. Okay, so tensile strength is a measure of how much force you actually need for that. So today's class is really, we're going to be looking at the relationship between those two things. So we introduced branching or side chains and cross-linking and chain length. Okay, we talked about some of these properties, these new properties. Okay, we're going to be looking at some other ones like melting point. Okay. As well, and how do they actually relate to each other? And you're the one that's going to come up with the relationship through a little experimentation in conjunction with taking a look at diagrams. So at your table, you should have diagrams which are unique to your table. So if you look at a table next to yours, it's not going to be the same. It's not going to be the same. That's not yours. So go ahead and grab what's on your table. And make sure, does everybody have a copy? It should look something like this. It'll look different for your group. So group one, you're over there. we're going to use you guys as the model today when we do a lot of our talking. Okay? Group 1 is going to be doing an experiment on plasticity. And they're going to become the expert on plasticity in the classroom. So you're going to be the expert on plasticity and the test that you're going to run. Now, their polymer, they have polymer A and polymer B, and they're off on the side. Okay? What you're going to do, now you don't have A and B. Some of you have B and C and D, E and F, et cetera, et cetera. What you're going to do is you're going to compare your two polymers to each other. Okay? You're going to take a look at polymer A, if you're in group 1, and polymer B, and you're going to do a compare and contrast. Now, one way to do a compare and contrast is through Venn diagrams. So if you turn your page to the back, you'll see a Venn diagram. Venn diagrams are great for organizing your thoughts. So what we're going to do is we're going to take that text, those molecular diagrams, and we're going to try to organize it into a clean, crisp diagram. Now, I'm sure you've used Venn diagrams before. So if you're working with polymer A and B, you would put A here and B here. If you're working with C and D, C here, D here. What are the properties which are different? What are the properties which are the same, okay? And which of the properties are different again for those respective polymers? Now, it's important to please, when you're using the Venn diagram, we want to hammer those vocabulary words home, okay? So make sure that you're using the appropriate scientific terminology. You have that vocab list in front of you, so please refer back to it as often as you need to. Okay, that's yours for today. So that's where you're going to start today. You're going to be taking your time, okay? Mull over the molecular structure, compare, contrast. What do they have the same? Ultimately, what is the major difference between them? Then what you're going to do is you're going to test the physical property that I asked you to test. In your case, it's, say it again, plasticity. What are you guys testing over here? Melting point. So we're going to see how the structure affects melting point. What are you testing over here? Tensile strength. What are we testing here? Elasticity. What are we testing here? Testing hardness. Okay, so each one of you has a unique physical property that you're going to be performing tests on, and you need to become the little resident expert within this classroom on that property and how the form of the polymer affects that specific property. Okay? You're going to be doing a small experiment. I give you very, very vague instructions. When you design an experiment, the experimentation should only take you 15, 20 minutes. Okay? Let's not go crazy here. Think of what makes valid experiments. Okay? We're looking for constants, constants, constants. And be ready to talk about those constants when you present what you did. Okay? You're going to need to record your data. And this data table here is for you and your data. And what we have here, this is a basic outline of a data table. And of course, you're going to have to add things to this. Okay, we talked about how you should be formatting your data tables. Okay, as you see here, modify the table as needed to indicate the dependent variable and the trials that were performed. Okay? When this is all done, now you're going to take a look at, all right, here's my compare and contrast, here's my data, how do they combine together? Okay? And when that's done, and you've established that, and we're strong on that, you're going to present what you did to the group. And we're going to ask them to see if they came up with the same conclusions as you. Okay? So you're going to make a claim, they're going to make a claim, you're going to be the expert, help. Okay? And we're going to see if we're in the right place. Okay, so I think about 4 minutes, 4 or 5 minutes, I'll give you on the clock. That should be a good time to really sit down and do a good comparison of your two molecules in your Venn diagram. When you have your Venn diagram completed, and your table has this completed, call me over. I'm going to check it. Okay? And when it's checked off, you get your stuff and get started. Okay, couple safety issues to note. Melting points, okay? There's goggles in there. Please make sure you have goggles and your hair is back, okay? I'd like you guys to wear glasses for yours, okay? Safety glasses, you don't need goggles.
You got it.
Okay? All right, let's go.
Sounds good.
Get to it.
So both
Compare and contrast. We're sitting. You're not going to start the experiment until you've compared and contrasted and created your Venn diagram.
The chain length is smaller.
I see. Polymer A.
We'll commit a merge. Just say that to start off with.
So A has a short chain.
So we can have something.
There's a guideline. Hopefully you're done and okay and ready to move on.
30. There's Sam. What's
I was about to like open that.
Yeah, me too. I was like, yeah. Oh, that's
Alright, so.
Polymer I is longer than J.
Okay.
Polymer I is longer than J?
Longer.
Neither of them have the.
Well then you write polymer J, you just write shorter.
Yeah. That's what I'm guessing,
Okay, shorter.
Good job, Ryan.
What'd you call me?
Good job.
What did you say?
I said good job.
You said something else after.
No, I didn't.
What'd you say?
We don't know anything else. So I guess we should count. 1, 2. Okay, I got 10.
So 30.
That's why I got 10.
Yeah, it's 10, but there's 3 of them.
So 30.
Yeah.
And then
There should be lots of
Adam has
similarities.
3.
So we're going to elaborate on those similarities. Okay. Think outside your vocabulary also.
64 carbon atom.
Well, let's really focus on that the main branch. Okay, as far as chain length.
Anything else about
Right.
like the characteristics?
So what are we identifying as our major difference? Branching. Okay, branching. So clearly, when we take a look at our structure, we see lots of branching, right? On this. So no branching and branching, short chain length, medium chain length. Let's look at that main chain, okay, for that chain length, okay? Is that main chain the same or is it different? Couple minutes, you should be finishing up. So what do we got?
For D and F, yeah, we said polymers, yeah, so
You said there's a lot of similarities.
both have cross links and there's no branching. And then for each side, we said how many cross links.
Okay. So polymer E, let's see your diagram. Polymer E, you have identified with
5.
5 crosslinks in this diagram anyways. Remember, this is just a model. Okay, and then, so we'd say lots of cross-linking perhaps. And in this case, less. Okay? Good. So I'll give you guys the green light to start your testing. Okay.
Come with me to get the stuff.
Would you say that
These are atoms, the ones that you said were very
This is a yeah, well, the carbons are on each
but do they
spot.
have to be carbon?
Generally, most of them are. No, they don't all have to just be carbon. In this case, they are. They're hydrocarbons.
I
Okay.
think hopefully
Is that what you said?
Yeah.
Okay, good. Remember, these are just models. So in reality, these things are going to be
patch because
thousands of monomers.
bad.
I wouldn't say carbon, more carbon. Well, let's not say. Let's look at our vocabulary words. They're both polymers.
Chain length.
So what?
Bingo. So they would have more mers, making a longer chain length. Okay, so
I has more.
So wait, do we
that's not what longer chain length is really what the focus is. Okay, so longer chain length, shorter chain length. What about things in common?
In this activity, you will test the tensile strength of 2 polymers.
Okay, good.
Secure the
So I think
polymer
you
to
guys
the
are ready to
clamp
go.
on the ring stand.
Okay.
Attach another
So
clamp
you
to
should
the
be
bottom of the
finishing up,
box.
I
Add
hope, at
weight
this
to the
point.
bottom clamp and see
If
the
you
polymer
haven't got a
breaks.
check
Continue to
mark,
add
you guys
weight
can
until
start.
the polymer breaks.
It's okay, one per group. It's fine. So where are we?
Well, they both cross-link, but the G has 3 and H has 5.
Okay. What do they have in common?
Is it the same?
Well, they both cross-link, but they're different
Right,
cross-link.
but what else do they have in common?
They're, well, I don't know off the top, they have like 3 lines.
So use the vocabulary.
They both have
Let's use the
they
vocabulary.
both have
Where's our vocabulary?
three polymer chains.
There's 3, in this model, there's 3 polymer chains that are shown, yes. What else? What else can we talk about?
We could say the side chains.
I don't see it written here. Where are you writing that? Is that something that's similar or different?
It's different.
Let me show me.
This one has 5.
Where do you see side chain on here?
All right, there's no side chains. There's
What's a
branching
side
off.
chain?
Okay, you weren't here yesterday, so go ahead.
Is it like a chain?
It's like these. It's like that,
Oh, no,
but
it's
then it's
like-
like going off the.
Yeah, it's like
Oh, okay, so it's like the first example.
Right.
Yeah.
Okay, so would that be a similarity or a difference?
that would be a similarity because neither of them have it.
Okay, good. So what else? There's one more you should be talking about. So we have side chains. No. We have
Alright, we'll start with
Wait, what has to stay dropping?
50. So yeah, just let it go.
It's not gonna.
Yeah, it's fine.
elaborate. Elaborate.
How much?
50.
Should we write this down in our notebooks?
In this one, as far as, well, these are going to be
Wait, don't do it yet.
monomers.
We've always 50, but they haven't done anything.
But as far as the other stuff, no, there's not a lot of other stuff.
So what are we trying to test?
Good.
How much again?
No, you have to wait it for like 10 seconds.
K is shorter. It has less elements. I mean, how many? Or less MERS. There we go. And then neither have branches and neither are cross-linked.
Excellent.
So we were wondering if that would have anything to do.
Good. You're good.
Great. We're breaking out the goggles. Is there a procedure on here, or do we just kind of make our own as we go?
I don't think so. I think we just have to go by
Okay.
the same
So
because we have to
let's procedure it.
make sure that there's just like same amount of.
Are you ready to start?
I know that we have a mass.
Yeah, so we have to weigh how much.
So Matt, put on the goggles and let's figure out how much roughly. All right, we'll put in. And
What else are we missing here? Okay.
Oh, okay.
There's 3 basic ones we talked about. Branching. So
and chain link.
cross-linking. Okay. So do we have cross-linking here? No. All right, we got a yes and we got a no. Which one is it?
No.
What makes you say that?
Because there's nothing linking them.
Okay, excellent. So there is no cross-linking. So let's make sure that we have that here.
Oh, sorry.
Yes.
Meter stick.
There's a meter stick right there on the side table.
We already have that.
Okay.
Oh, wait. Oh, I already had that.
We already have that.
Mr. Turek, we had that.
Oh, okay. All right.
Can we start?
Yeah, go ahead.
Where's our stuff?
Didn't break.
So we're gonna give you about 12 minutes. Not everybody's going. Yo, I'd like you to do the appropriate amount of trials that you can.
So more seconds. I think 10 seconds is
Okay? Those are it. This is, okay, so this is tricky. I'm sure you've never used this before. Okay? Right here, this is in, right here, when it's at 1, that's 1 centimeter. So every line is a
Stop moving the
millimeter.
table.
So right there would be 1
Yeah, so it's
1 millimeter, 2 millimeters, 3 millimeters, 4. That would be 5 millimeters right
That's
there.
a constant.
So,
What else are the constants? Same amount of whatever it is.
No, it'd be like, yeah, you have to use that to see how far deep it went down.
yeah, but
Where's that big
What was the one we just used? This one?
this one. This one, right? This is 2,000.
Wait, what was the one we
That
did?
would be,
Before that.
so yeah, those are millimeters. That would be a centimeter, right? When you say that would be about a centimeter?
2009?
Okay, so that right here, 1, that's a millimeter. 2 millimeters, 3 millimeters, 4 millimeters, 5 millimeters. Okay?
So we're doing 50. So which
Yes.
thingies?
Kind of messed up there, but
So did I, but
All right, so make sure you have a discussion
you have to
as
put
you're doing these
measurement
experiments, because
or
I'm going to
deep
ask you these, so make sure you,
because we're measuring how deep
about
it goes.
constants,
all right.
okay? What is it that you're going to keep constant to ensure the validity of this experiment?
We have to
So what can affect,
Where we drop it from?
okay,
I
and
was gonna say 50.
what else?
50 cents.
What else?
How many times you drop it?
What if you drop it on?
Oh, what surface we drop it on?
I think we should do the floor because I don't want
said
to
the
knock
table.
that over.
Okay. All right, good. You're thinking constants. Good.
Are we writing that somewhere?
So now we're good to experiment?
Yeah, I guess.
What kind of experiment constants have we talked about? Constants. How are we going to make this a valid experiment? So the only thing that's changing is,
That the polymer.
okay, so what are we going to keep constant? What are we going to keep the same?
Same.
Skull plumb bob.
Okay, same polymer.
What else?
The same height strap.
Okay.
Constants.
Okay, good.
Okay,
Keep
so
those in mind. Any other questions?
like, no, never mind. No.
I'm gonna write that down.
All right, let's do it, guys.
Start timing.
Why don't you start with this guy right here?
That's polymer J.
I'm gonna lead you in that direction.
Okay.
If I were you, it might be a good idea to take
So
there's some
step
chalk
one,
over there.
we poured it into.
Mark it so you know
Figure it out.
Where to
where to put that, so you don't miss it.
What if we do miss it though?
Okay.
It's too bad. Wait, I just want to see where
Okay.
this thing goes.
That's okay. There's lots of these. I have lots of
Right in the
these.
middle.
Wait.
So if you want to do multiple trials, you can do
Wait,
multiple
just,
trials.
No, like,
Okay, so
you
next
drop it
one.
without that thing.
Where-
Watch out.
Okay, go ahead.
Do it really slow.
No, watch your finger. There you go. Alright, so like,
So it's like right there.
And clip it, or
Yep.
and then
Polymer.
Palmer. And then we put each of these on for 10 seconds.
Okay.
And then wait for.
Wait and see if it causes it to break.
Yeah.
So if I were you, I'd make little things about like that. Okay. So let's put it up there. Let's pinch it up there. If you want, you know what might work a little bit better? I'll be right there. What might be a little bit better is if you had it like this.
We're testing every.
Okay. So it's slip through. So if we could try it like this. There we go. Pinch it off. Okay. Okay. Now attach the one on the bottom. So you're looking at just about 8 minutes. So get in a few trials. Don't pull on it. Now somebody should start getting that F ready. A good chunk of F ready. That's good. That's good.
We start off
So,
with this.
no wait. Is it breaking?
No.
No. Okay, and you gave yourself what? A time frame?
Yeah.
That's good. So you're thinking constants, yes? Constants, because I'm going to ask you about constants.
Well, the time would be constant.
Okay? So, well, go ahead, add some weight. Now, I'm going to say you're probably going to want to add a little bit more than that. You can start there if you want. Sure, start with that one. There should be a little hook on there. Okay? So you can see it starting to stretch. Is it going to break, though? And that's the key. You gave yourself, is it going to break in 10 seconds? And that's good. And then, so what you can do is keep adding weights. Now, if you look, there's a little spot right there, so you can just kind of add weights. See that? And then you just add up your little, that was 50, and that's 20, so that would be 70.
Okay.
Okay?
Alrighty. Thank you.
How we doing? Yes.
No, I'm pretty sure we got it. Alright,
How
so
much is that?
you see how long this is, right? And then it goes to 21. So then you rip it and see where it snaps, and you measure from this end, because that's how far.
How much did it stretch?
Yeah, how much-
What was the total stretch?
I got you.
What was the total stretch?
So you start out here, and you stretch it. So like, see how far it
Yeah,
goes?
how far are you at now?
Oh, okay.
How far are you at?
24 and it started at.
Okay.
So
Alright,
3
So
centimeters.
you were able to stretch it 3 centimeters before it broke.
I think we did these two right.
That's okay.
We got more?
Hurry, stop yanking it there.
Know your time. You got 6 minutes. So see how many trials you can get done. It broke.
I think you guys should
All
work
right,
on that.
good. So then you reach, you know it's okay. How much force it takes to break it?
Dang, that hurt.
Using my slow camera to
Are you kidding? Wow, that's a good use of technology. I love it. Great idea. How we doing? Are you hitting it?
Yes, both times. I haven't missed yet.
You haven't missed yet.
Knock on wood.
Okay, right there.
Thank you.
How are you measuring your height? What are you doing to ensure constant drop height?
There, when it's touching the thing.
Okay.
Ready, guys? Wait. Yeah. Hold on, it's not. I don't think it's on. Yeah, it's on. Oh.
It's all right, just move it.
You ready?
A little bit more.
Have we done the other ball? Also? All right. Note your time, okay? Note your time.
The bigger one.
Note your time. Hey, what? How we doing?
That was bad.
It's up to you.
Or when it starts, because we already have starts,
almost done.
but the
Whatever you choose,
Okay.
be consistent. Okay? Constants.
Okay.
So what are you finding?
We found that
Okay.
Melted faster.
A lot faster.
Okay. What did
And
you
it
have?
has less MERS.
What do we have? Let's use chain link.
Okay. It has a shorter chain link.
It has a shorter chain link and
It shows that it had a
Yeah.
lower melting point because it was
Just from
shorter chain link. Obviously, if it has a higher chain link, it's made up of more MERS.
I don't know how obvious it is, but we'll get to that. So how many trials have you been able to do?
This is our first.
Okay. So maybe we can do a second one so we can verify our results.
Okay.
Okay. Now are you keeping the amount the same?
Yeah.
Okay. Using
168 grams.
168 what? 168 grams. That's a lot of grams. Oh, okay. 1.68? Note your time. Note your time.
you didn't put any weights on it.
It broke.
So it has no.
So no weight.
Well, there is
Well,
weight. I
depends.
understand
Well,
that.
that clip had.
Do a couple trials. Now, is this as thick as the other one was?
No.
Maybe that's something you might want to. When you did your, how thick was that first polymer when you tested that?
Okay.
That
And
might.
it was shorter too.
How we doing?
Yeah, like that. But
Okay, good.
And you want us to do this, and then we're sharing with us.
You'll share out, yep. So what you can start to do as you're finishing up right now is grab a whiteboard, grab a black marker, and start making a big, fill up the whole thing like that, like the one that I have there. If you're close to finishing up, one of you should grab a whiteboard and a marker and start making a big data table. Grab a whiteboard, grab a marker. That's okay. You guys, that's okay. You guys can go ahead and do it.
First trial
Okay.
one.
Will not
It held 1,109.
So are you reading this correct? Let's see. Let me see.
and the other one, I don't know how much that clip weighs.
Right? Yeah.
Yeah, 1 millimeter.
Wait,
That's
millimeter?
Yeah, that's 1 millimeter right there.
Oh, my
When you get to
bad.
one, that's okay. You can fix that.
It's okay. Alright, still, just change it from centimeter to millimeter. My bad.
I told you it was.
If you get all the way around, it's 1 centimeter.
Oh, okay, my bad. I'm sorry. guys.
You see, Bess, it's okay. We all make mistakes.
I'm sorry.
Get up next time. Try hardest.
Alright.
I told him that it was millimeters.
It's 1 mm.
One of you should probably start grabbing a whiteboard and start transferring that data table to a whiteboard. Just under 2 minutes.
Whiteboard.
If you haven't grabbed the whiteboard yet, grab a whiteboard, start transferring some data.
Since trial one.
There's one over there.
Okay, so it's on melting point in general, right, Laura?
Yes.
Okay, so melting point.
The first one was 1 The first one was milk. We we copy this data table?
Alright, 1, 2.
So I'd like you to finish your experimentation now. Finish up. If you're in the middle of a trial, finish that trial. If you only got through one trial, that's fine. That's fine.
Alright, first one's 3 centimeters.
Wait, we don't need to write.
Put the data table there. Just the data table. So let's get that data table up.
I thought you weren't supposed to.
Well, it's definitely
Wait.
4 centimeters. 11. 11, 13.
Oh my god,
And top average.
You just put them off to the side. When you're done with your equipment, if you could just put it off to the side.
But
You're running out of space.
Ica.
What was the other one?
It's turning. It's turning. It's let it rip. Hold on. Quickly. Quickly.
So I can do 2 trials?
There you go. And there you have it.
You put an
There you have it. Okay, you have 5 minutes now. 5 minutes.
Should I put this in there?
Yep.
No, it's good. It's fine. Or you know what? Yeah, sure. I thought there was we needed to put something else there. My bad. Yeah, sure.
So, we got our data. So now what I want you guys to do, okay, everything's back, is sit down and make a claim. Okay?
Okay.
How does the structure affect that? Okay? Do this by yourself, and then you guys, when you have it done, you guys can talk and make sure you're ready to go. So we have our data. Let's not, okay, we're not, just get it raw, get it up there, okay? I want you to spend more time analyzing. So now that we have our data, individually, I'd like you to sit down and look at your Venn diagram. What is the major difference here? What happens to our data? And make a claim, okay? How does the structure of the polymer affect the characteristic? In your case, you're looking at elasticity. As any claim, make sure you support with evidence, okay? All right, we gotta get this. Let's get this out of here. Let's get this out of here. And let's have a seat. It's okay. One is better than none. So now that you have your data, I'd like you to make a claim, okay? So now you're gonna make a claim.
Is that the elastic I'm smelling?
And then we have to do for examples.
Wait, should it be hard or How do you start it?
Or something that's in the polymer that makes it different from one than another.
I'm not sure what you mean.
Okay, so like, well, clearly, this one does more than that
Well,
one.
yeah, well, what was different about them? You identified the difference. What was the difference between those two polymers?
Different amount of cross links.
So,
Like we can make a claim
I
that
think there are more cross links in H.
that polymer H.
no, we're trying to connect those two now.
That
We
polymer.
made that claim here. Now you tested the elasticity. So how do you think the cross-linking affected the elasticity?
Are we writing this separately?
You're writing this separately. We need to get writing. We need to get writing.
This?
Yep.
Okay.
Okay. You guys made a nice mess here. Good. Science is messy. I will take care of it. So you guys have to make your claim now, okay? Make your claim. How does the structure of the polymer affect, what were you studying? Plasticity. Okay.
Was that actually based off how this?
Yeah.
So that's
Yes.
okay.
Yeah. A was which one? The black one or the clear one?
Clear one.
Okay. So compare and contrast.
So
Have we made our claim yet in writing? Okay. You're working on your figure. You haven't made it yet. We need to do this.
Where should we put our claim?
You're not. You're not. All I want you guys to do. Oh, look at you. You're very thorough. I actually have this to show.
Oh.
So that's the part. That's the only part we need. That's
Easier
fine.
it will be to get through.
Let's make that claim.
We did harder for one of them. Like those we saying that the longer the chain length is, it will be the polymer will be harder, and then the shorter the chain length is, what should we say?
Well, if it's not harder.
It's softer, but we said it'd be easier to penetrate.
Okay.
And then we would say this is shown through
Okay, thank you. So what are we providing then?
evidence.
Do I want to repeat that for you, Nick?
Hold on. Give me 2 seconds.
The longer the polymer chain length is, the harder it will be to penetrate it. And the smaller, the shorter the
The longer the polymer chain length is, the harder the polymer is. And the shorter the polymer is, the easier it will be to penetrate.
this shows.
Polymer chain length, my bad.
During our experiment, we were able to calculate this polymer K takes less time to melt, or has a more.
This shows.
This is shown through.
Proved by.
No, we can say this shows.
No, but then we gotta do this.
I know. Right. Let's see how A is branching and this one's regular.
Because in the data it shows the polymer
Chain.
This one's really strong.
weight of 1,100.
So this shows
and
regular chain.
1,000.
This shows regular
It's stronger.
polymer chain.
What's
Make sure you guys are on the same page because you're going to be. The class is going to make a claim. You're going to
We're
agree.
So, are we presenting all of them? Or?
We're gonna agree to disagree.
No, you should make a consensus. Do you all agree upon which one?
All right. G,
And are we just
G bounced
representing one
higher
of them?
because it had more cross
You're going to
links.
explain what you did.
Yeah.
H jump.
I mean, we're going to ask the class to make a claim.
Yeah.
So it had
And then
more
tell us
elasticity.
tell them what ours
More or less.
Do you agree?
So it didn't,
with them.
didn't have as much
Okay.
form. It couldn't form.
How we doing?
All right. So.
You got evidence in there?
Yeah.
Excellent.
I go to the bathroom.
Frankie, it's 2 o'clock. It's 2 o'clock. It's past 1:45.
Wow, this is flying by.
Yeah, it is.
Hey, time flies when you're having fun.
Sir, I like your pants.
You guys forgot this one?
Okay.
Plus this here's 370.
Okay. So, what I'd like to do here is just wrap up what you have, please. Wrap up what you have. And then I'm going to model for you what you're going to do. Okay? So wrap it up. Make sure we're good.
Alright, so who wants to put a line?
Penetrated 1 millimeter deep by the plumb bob, but in trial 2,
Okay. Freeze. 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 All right, so there's one station which you guys didn't do, okay? Nobody in the class did, and that's me. Yay. Okay? So what I did, I actually did this, okay, is I looked at polymer C and polymer D. Now, when you look at polymer C and D, what you can see, okay, is the length is the same. Okay? So what they have in common is their chain length. Okay? Another thing that they have in common is the fact that there are no cross links. There's nothing linking this polymer to this polymer. There's nothing linking this to this. And ultimately, what then you have here is a difference in side chains or branching. So polymer D has substantial amount of branching or side chains, while C has none. And what I did was I looked at how the branching then affects density. And the way I did this, I'm gonna ask you to just kind of explain what you did. It's difficult to actually find densities of plastics because all of them, or a lot of them anyways, are less than 1. And a lot of time we find density, we put them in water, and we use water displacement to find volume. It's tough to do. So what I had to do is I had to make known solutions. So I made solutions 0.92, 0.90, 0.88, all the way up to 1.0. And I put the polymer in, and it's just hard for you to see, but this one right here illustrates one of them sinking and one of them's floating, okay? So you can see a difference in density in this liquid. So the data that I have from this is right here, okay? So this is the data that I have. So what I'm gonna ask you to do, this is what group 2 would have done, is turn in your packet to where it says group 2. Density. Density is a measure of the mass per unit volume of an object, okay? It determines if it will float or sink in another object. Okay, so what I want you to do in that left column, what is the difference? What did I identify as the difference between the structures? What was the difference that I identified in the structure? So write that down in the left column. Just one. What is the difference? Now here's my data. Polymer C has a density of 0.94. I did 2 trials and averaged it. Polymer D has a density of 0.91. So what I'd like you to do in that second box is make a claim. What I identified was side chains. How does side chains affect the density of the polymers? Go ahead and make that claim. Here's the data. How does side chains have a brief conversation with your table. Talk to your table.
So the one with the branching has a lower density rather than branching polymers have lower densities.
The side chains make it have more density because it's 90.94.
Wait, branching polymer had more density? Yeah, it's polymer. They have a lower density? Yeah, they have a lower density. Because polymer C has more density.
Okay, so we'll stop right here. Some good conversation that I heard. Does any table feel confident in their claim? Table 1? Go ahead. Sure.
Alright.
What was the claim that you made based upon the structure and the data that I showed you?
Alright, we said side chains add more density to an object. With side chains, the density was 0.94, and with the branching was 0.91. So that
Okay. Go ahead, make that claim then. So what is the relationship between side chains and density?
More side chains and more density.
More side chains is what he said increases the density. So now, if this was your group, what you're going to do is you're going to either verify his claim or refute it. Does anybody want to do that for me? Table 3, would you like to verify or refute?
I'd refute it.
You refute the claim.
Yes.
She doesn't agree.
Okay.
Okay, go ahead.
I say that it doesn't affect it because, or no, it affects negatively. There we go.
Okay.
Because C has no branches basically, and it only has a 0.94 density, whereas D has the actual branches and it has the 0.91 density. So then that's less.
Okay. So we have a different idea. Let's get a tiebreaker. Table 4. What are your thoughts?
My table agrees with Taylor because polymer C turns out to have more density, 0.94 compared to polymer D, which only had 0.91. And as you see in the diagram, C has no side branches, but in the data table, it has a higher density.
Okay, excellent. So, and that's what we have. Okay. So, if you think about branching, think about a tree. If you're going to stack trees together, density, how compact can you get it? If you took all the branches off a tree and you laid them on top of each other, compared to a tree where all the branches were still attached and you tried to lay them on, which can you pack more into? The trees without the branches on them, or with the branches? Where can you get them more packed together? Without. And that's what you see. Because you have no side, you can pack those things in there really tight together. Okay, you guys are up. Let's share. We're only going to have time for one today, and we'll continue this tomorrow.
Alright, for our experiment, we had polymer A and polymer B, and we had to use rulers and see the plasticity of it. So we would rip it and hold it in front of the ruler and see how far it would stretch until it ripped. And polymer
Okay,
A,
so let's take a look at A and B, shall we? So what did you notice about A and B?
well, polymer A only stretched 3 centimeters before ripping.
Let's talk about the structure.
A has branches and side chains.
Okay, good.
And then B was just a regular chain link.
Okay, so go ahead.
So A stretched 3 centimeters before ripping, 4 centimeters, 3 centimeters. And then B stretched 14 centimeters, 11 centimeters, and 13 centimeters. So polymer B had more plasticity.
Okay, so polymer B did have one. So let's make a claim. Go ahead and try that. Make a claim. How does the structure of the polymer affect plasticity? Go ahead. You're ready. So you're at group 1 now.
Thanks, man.
That's it. What's the word? What's the vocab? Plastic. Plastic. More plastic. Okay, talk to your table. Talk to your table.
Okay, so I said
Polymers will have more plasticity.
It's okay.
With no branches
Talk
as
to your tail.
opposed to with branches. This is shown through.
Polymer B had more plasticity because, as you see in
Chris,
the
what do we have?
diagram, polymer A has a lot of side branching, but its plasticity
Okay,
is
that's
only
fine.
3 centimeters
Yep, so what do we-
compared
what do
to
you see?
polymer B, which has no side branching, but its plasticity is still much greater than A's.
Let's look at that data. What is that data showing you?
Because in the experiment, polymer A only stretched 3 centimeters without side chains, while the polymer B stretched 12 centimeters without
We're using the word
side
plasticity.
chains. Therefore,
Plasticity will be.
Okay, very good. Table 6, we haven't heard from you
side
yet.
chains.
Let's hear your claim.
All right.
Go ahead. Quiet down, please.
You got it.
Quiet down, go.
Alright. Polymers will have more plasticity with less branching because in polymer B, that had no branches, had an average of 2.6 centimeters.
12. That's 12.
12, my bad.
Right.
0.6 centimeters of plasticity. And polymer A had a lot of branches and had an average of 3.3 centimeters.
Outstanding. Okay, verify that? Yes? Okay, we're running out of time here. Good job. Here's the deal. Let's sum this up. Now, we haven't had time to go through all of these, okay, but clearly we can see that there's a relationship between the way these polymers are structured and how they act. For homework, turn to the last page. I'd like you to find a polymer at home. List, feel it, stretch it, and see if you can find any information about side chains or chain length. Try to make a connection and bring that in for me tomorrow.